Hello, this is Geometry, Lesson 3-5, Topic 3, Lesson 5. This is the last lesson of the topic. It's about symmetry. So in this lesson, first, we'll describe the rotations and/or reflections that carry a polygon onto itself. Second, you will predict the effect of a given rigid motion on a figure. Third, you will identify types of symmetry in a figure. Okay, let's look at explore and reason. Look at the kaleidoscope image shown. Then consider pieces A and B taken from the image. Look at pieces A and B. This is a pretty kaleidoscope. Part A, how are piece A and piece B related? So kaleidoscopes are these patterns, these images with a pattern, okay? How are piece A and piece B related? Can you describe the rigid motion that you can use on piece B to produce piece A? Okay. Or if you cannot describe one rigid motion, part B, you can describe a composition of rigid motions that you can use on piece A to produce the image. Okay. And then think about how many rigid motions did you need? Minimum to produce the image from piece A. Can you think of another composition of rigid motions to produce the image starting with piece A? So thinking about all the rigid transformations you've learned so far, can you describe a composition of rigid motions from piece A to piece B? Okay. First of all, you need to notice that piece B is about half, right? It's half of piece A. And so if you reflect piece B over the straight edge over here, the horizontal side here, and copy itself, piece B and its image together should form piece A, right? So in part B, you can also say you can rotate piece A about its pointy edge over here to produce the image. Okay, let's record those answers now. Okay, so part B is about how you can make a copy of piece A. Okay, so you can just rotate, or you can reflect and translate, but rotate would be the easiest one. Rotate about 45 degrees or 90 degrees from to this point so that it could produce another image that could be the same as piece A. Okay, so how many rigid motions did you need to produce the image from piece A to get the whole image over here, the whole kaleidoscope? How many of these? So you can maybe divide your flower into sections. Okay, that's 1, and that's 2, 3, 4, 5, 6, 7, 8, right? If you divide 360 degrees into 8 pieces, that's how you get 45 degrees. And so 2 of them will make 90 degrees together. Okay, 4 of them, 180 degrees. And then all 8 of them would be 360 degrees, right? So then you can say it needs to be rotated how many times? Well, starting from here. 1, 2, 3, 4, 5, 6, 7. You just need to copy it 7 times to make total of 8 pieces, including your piece A, right? So 7 times, rotate 7 times to produce the image. You could also reflect piece A 7 times so that you have a reflection over here, and then reflection over this edge, reflection over that edge, reflection over that edge, reflection across this line, and so on, right? But it needs to be 7 times at least to produce the image of the whole kaleidoscope. Okay, Let's record that down. Okay, it needs to be either rotated or reflected 7 times. So let's keep in mind this question for throughout the lesson. How can you tell whether a figure is symmetric? So we're going to talk about symmetry, and this is one of the examples of symmetry. You have the same kind of pieces throughout the whole circle, right? So if you find the same pieces somewhere else, that is going to be symmetric. Let's look at example 1. Identify transformations for symmetry. What transformations can be used to map the figure onto itself? Why can some figures be mapped onto themselves? So we're going to define symmetry. A figure has symmetry if a rigid motion can map the figure onto itself. That is your first definition. Okay. Reflectional symmetry is a symmetry for which a reflection maps the figure onto itself. Okay. So first, symmetry is when a rigid motion can map the figure onto itself. It needs to be a rigid motion. Reflectional symmetry, symmetry for which a reflection, you need specifically reflection to map the figure onto itself. So for example, this figure, you have lines of reflection M and N to reflect the shape onto itself. The line of reflection for a reflection symmetry is called the line of symmetry. Okay, the reflections for these two shapes. Actually, this is one shape. This has two lines of symmetry that you can map onto itself. You can divide it like this and map onto itself by folding it by half like that, right? Or you can divide it by this line horizontally, and you can map the other piece onto the other piece. Okay, the figure has rotational symmetry if its image is mapped onto the pre-image after a rotation of less than 360 degrees. Okay, so if this shape can rotate 180 degrees to map onto itself, yeah, it has a rotational symmetry of 180. Okay, also has rotational symmetry of 360, but rotational symmetry is going to talk about your least angle, where you can map itself. Let's look at try question part 1, A and B. What transformations map each figure onto itself? Do we have reflectional symmetry or rotational symmetry? Okay, do we have a symmetry at all? Look at the lines where you can divide it from or fold it if it were a paper and get the exact same shape onto itself. You have a reflection over a horizontal line right here and vertical line through the center. Okay. Or can you rotate? You can rotate 180 degrees to get exactly the same shape. Okay. If you have specific points that you want the orientation to be, it's not going to work. But as far as shapes, it's not gonna be a problem. Okay, so part A, you have reflection over vertical and horizontal lines through the center, and also you have 180 degrees rotation to map each figure onto itself. What about part B, the smiley face? Can it map onto itself? Yeah, there's only one way to map onto itself. If you divide vertically by half like this into the center, you can map your smile exactly onto each other. You can map your eyes onto each other because that smiley face is symmetric vertically. Okay, so you're gonna say reflection over a vertical line through the center. look at the next page. Example 2, identify lines of symmetry. So now that you figured out how to write symmetric lines where the line of symmetry is, we're going to identify more lines of symmetry using different shapes, okay? So look at this hexagon. How many lines of symmetry does a regular hexagon have? Regular means they all have the same size, they all have the same angles, okay? So you can cut the hexagon exactly in half through one point to the opposite point, right? By connecting a line through these 2 points. And you have how many lines? 1, 2, and 3 lines total. And that's going to be your lines of symmetry. So a regular hexagon has 6 lines of symmetry, including the line that goes through each opposite sides in exactly half, okay? So don't limit yourselves by thinking about lines that goes through points or vertices. You can also think about lines that go through different sides and cutting them into exactly half, okay? Also remember that lines of symmetry are not necessarily horizontal or vertical lines. It could have slopes. Let's look at this try questions. How many lines of symmetry does each figure have? What do you see? How do you know whether you have found them all? Okay, first figure out the lines of symmetry. What do you see? In this rectangle, how can you cut them in half? Okay, you can cut it horizontally by cutting through the center. And then you can cut through horizontally like this. Can you cut it diagonally like this? No, because if you fold it, this one maps like this. It's not gonna be symmetric like that, okay? So only 2 lines of symmetry for a rectangle. Or about this trapezoid. We cannot cut them diagonally either. Can we cut it horizontally? No, the bottom side, the bottom base is going to be longer than the upper base. So you can only divide this trapezoid by half vertically through the center. So one line, only one line of symmetry. Okay. And so think about all possible ways. And if there are no other ways to fold them and map them onto itself, that's when you know whether you found them all. Example 3, identify rotational symmetry. For what angles of rotation does the figure map onto itself? So we want to find the exact angle where we rotate the figure to have symmetry onto itself. Okay, so these were the lines of reflection that we're looking at, right? Now we're thinking about rotation. Okay, look at part A. This triangle is an equilateral triangle. It has the same sides and the same angles. So first, you're going to find angles of rotation about the center that map this triangle onto itself. If point A maps onto point C, that would give this triangle the same shape, right? So you have total of 3 points total, and you have 3 angles total for this rotation, okay? In order for point A to map onto C, you need to rotate 120 degrees. So a rotation of 120 degrees creates an identical image with vertex B at the top, right? Then it would be B here, A, and C going over there. A rotation of 240 total, right? Should move point A over to point B, and point B over to point C, and point C over to point A, right? So you have rotation of 120 and 240 until it goes around full circle. Look at a parallelogram. Can you rotate 90 degrees? No, this doesn't work, right? Can you rotate 180 degrees? Yes. Is the orientation going to be the same? Yes. Follow your points. Okay, the distance of rotation. Yes, it's going to work. The type of symmetry for which there's rotation of 180 degrees, like this parallelogram, that maps the figure onto itself is called a point symmetry. So in this case, if you have a rotation of 180 degrees, you can call it has a point symmetry. This parallelogram has a point symmetry. Okay, that is a technical term. Let's look at triad number 3. Part A. What are the rotational symmetries for each figure? Identify the rotational symmetries. Does each figure have point symmetry? Okay. So keep in mind, this is specifically for rotational symmetries, not reflection. Okay. So can you rotate this from this point to that point? Yes. So what angle would that be? Think about the angles, the center of rotation over here, from here to here, from here to there, from here to there. You have exactly 90 degrees, 180 degrees, 270 degrees until you hit the full circle, right? So you have a 90 degrees, 180 degrees, 270 degrees. And does it have a point symmetry? Because you have a rotation of 180 degrees, yes. The figure has point symmetry. Okay, part B. Can we rotate this? We can rotate this end to this end, right? And so, yes, it has 180 degrees rotational symmetry. And we can say, yes, it has point symmetry. Right? All right, example 4 on the next page. Determine symmetries. Look at this flower. This is a cute flower. Did you know that a lot of flowers have symmetries? What type or what types of symmetry does each figure have? How many sections can you divide this flower by? How many same sections? Right? A line through the center of a petal is a line of reflection. So if you cut it this way, you can map this onto itself and they're going to look the same, right? So each line of these symmetry would work. So how many lines? 5 lines of symmetry. What about rotational symmetry? You can divide each petal like this, right? How many petals do you have? 1, 2, 3, 4, 5. Divide 360 into 5 different, into 5. And then you get each angle as 72 degrees, okay? So if you rotate each petal 72 degrees, it maps onto itself, okay? So this flower has a reflectional symmetry with 5 lines of symmetry. In rotational symmetry for angles 72, 144, 216, and 288. Okay, you did not include 360. That is how you write the answer for this type of question. What type or types of symmetry does each figure have? You need to define reflectional symmetry and rotational symmetry if you have them, okay? All possible symmetries. Part B, you're including this point, right? If it were just the squares and this rectangular outline, you would have symmetry. You would have reflectional symmetry. But these 2 points make it impossible to have a horizontal or vertical or any kind of symmetry we have, right? Okay. No lines of symmetry can be drawn because these 2 points don't exactly lie symmetric to each other. Because if we make the 2 points symmetric, if we draw a line like that, this point is going to map here, not over here, right? That's not symmetric at all. Okay, and the squares don't match at all either. Okay, so no reflectional symmetry, right? Rotating the card 180 degrees, though, it should create an identical image. So this could be in place of this, and this could go here by rotating 180 degrees. Okay, but not reflectional symmetry. Reflectional symmetry does not work. Rotational symmetry works. So it only has rotational symmetry or the point symmetry. Okay, look at a square. Think about the square. What symmetries does a square have? Think about a square. How many symmetries do we have a reflectional symmetry? Yes, we have a horizontal one, a vertical one, and the diagonal ones. So total, we have 4 lines of reflectional symmetry. Okay. And then how many do we have a rotational symmetry? Well, at this point can go here or here or here, right? So what angle would that be? Look at the points. Look at the angles that are formed by these points. Okay, it's going to be 90 degrees, 180 degrees, 270 degrees, and yes, it has a point symmetry. So you have rotational symmetry of 90 degrees, 180 degrees, and 270 degrees, and also point symmetry. Okay, list all the symmetries you have. And the last example, okay, is going to be using symmetry. Now that we've learned all kinds of symmetry, now let's look at a word problem. A company CEO wants a new logo that looks the same for each rotation of 30 degrees and uses the 3 company colors. What are some possible logo designs? Okay. So given this task, think about the symmetry you can make. Consider different elements of the design. Start with a polygon that has a specified rotational symmetry, 30 degrees, okay? Which means it should map itself at every 30 degrees rotation. So how many 30 degrees are in total 360 degrees? You can divide 360 by 30 and say, oh, I have 12 total of 30 degrees in 360 degrees. So that means how many sides might you start with? Could you start with? Okay, these are all going to be 12. So that's going to be dodecagon, right? 12 a polygon with 12 sides is called dodecagon, okay, or regular dodecagon. And now we're going to consider how the colors can be used so that each section is the same. So we're actually designing each section, just 30 degrees of this section, okay? So we can design it to be very complicated like this, or a little bit simpler, or very much simple design. So these are possible designs you can design for this company. These are just examples. You can make up your own design, but you have to copy and paste it with the same design for all 12 tiles over here, okay? So number 5, what's a possible design for a circular logo? It has to be circular that looks the same for each 60 degrees rotation and uses at least 2 colors, okay? So think about these. It doesn't have one correct answer. It could be any design with a circular logo. Okay, it has to be circular, but they need to look the same for every 60 degrees rotation. So how many 60 degrees is in 360? 6. Good job. Right. 6. And so yes, you would divide your circle into 6 pieces. Okay, I know that's not accurate, but wait, is that 6 pieces? No, that's not. That's 8 pieces. Gonna divide this into 3 and then divide each of them into halves, and that should be 6. There we go. Okay, so you're gonna design a piece, at least 2 colors. I'm gonna say, oh, this is, they're gonna have a blue, kind of a outside circle, a border outside, and then another blue. Okay, it says at least 2 colors, and I'm gonna color yellow for the other things. There we go. And then I can maybe put a heart because I love hearts, or should we do a star so that it looks similar to Captain America? Okay. And all the stars actually have to be symmetrical, and let's assume that all these stars are symmetrical, okay, even though they do not look symmetrical. Okay, so you get the idea. So this would be a possible design for a circular logo. It's circular. That looks the same for each 60 degrees rotation. 1, 2, 3, 4, 5 rotation will make a full image. All right, so let's summarize our lesson. We learned about symmetry today. We have 2 kinds of symmetry, reflectional symmetry and rotational symmetry. Okay, when we use reflection to map the image onto itself, that's called reflectional symmetry. When we use rotation to map the image onto itself, that is called a rotational symmetry. And for reflectional symmetry, you have to specify the line of reflection. For rotational symmetry, you have to specify the angle of rotation. All right, that was our last lesson for the topic, which was symmetry. All right, I'll see you later. Bye.